What I'm going to present to you today are a bit of my work on spin polarized electrons completely out of equilibrium, where the spin polarization is obtained not through a Zeeman splitting in equilibrium, but one in which we have essentially a spin polarization that's derived purely through injection. And then what I'm going to talk about mostly are the consequences of these spin polarized, the transport of spin polarized electrons in the presence of magnetic fields, and also, of course, under the influence of the details of the semiconductor host, which in this case, of course, is silicon. The primary motivation, or I should say, at least the original motivation for work of this kind really came about through the suggestion that one could make semiconductor devices akin to field effect transistors by making use of non-equilibrium spin polarized electrons from a kind of source to a drain through which the spin polarized electrons would pass through a channel where the spin could be manipulated with electric fields, much like charge is manipulated in field effect transistors. For this reason, silicon appears to be also a good material to work with, particularly because, as again many of you know, the spin lifetime is extremely long. So I should not be telling you anything new here. The sort of basic reasons why silicon has a very long spin lifetime are due to the fact that the coupling of the intrinsic angular momentum, the spin, is very weak to other degrees of freedom. The angular momentum associated with orbital motion in the spin-orbit interaction, also due to the fact that at least in naturally abundant silicon, most of the isotopes have no nuclear spin, so a hyperfine interaction is weak. And furthermore, due to a lattice inversion symmetry in the presence of time inversion symmetry, you have degenerate spin states, and so you don't have the same kind of relaxation processes which give rise to short spin lifetimes in, say, compound semiconductors, which are not centrosymmetric. What I want to first do is tell you a little bit about the difficulties of actually obtaining non-equilibrium spin transport. And then I'll go on to the techniques that we use to circumvent those difficulties and show you several of our more recent results. So again, we're not going to spin polarized electrons simply by applying large magnetic fields and going to low temperatures such that the thermal energy is on the order of or less than the Zeeman splitting, as is commonly done in many magnetic resonance techniques. Here we're going to use an external mechanism to inject spin polarized electrons. Now, the kind of direct, one might even say the naive approach, the way that one might come up with to do this at first, when first approaching this problem, would be simply to take a spin polarized source, a material which has an imbalance of spin up and spin down electrons even in equilibrium, and just take this electron population, which is already spin polarized in equilibrium, and push them across an interface into this non-magnetic material, silicon. And I'm going to tell you about the consequences of analyzing this process, and then show you that this is actually not going to work, and again, show you how we circumvent this. So the way that I'm suggesting here that you might approach it is through ohmic injection. We would propose then to take a ferromagnetic metal, one in which there's more spin up than spin down, and just form an ohmic contact with our silicon, apply a voltage, and then expect perhaps that the imbalance would be maintained across the interface. So first we have to remind you of how ohmic transport works. This is a process which is driven by a gradient in electrochemical potential, and it's proportional to the conductivity. So here what I have is a kind of band diagram in which I'm plotting the potential energy on the vertical axis and distance along the horizontal axis. And here what I have is a very simple junction between a metal, which has a high conductivity, and a non-magnetic semiconductor, which has a low conductivity. And so, of course, the current across the interface has to be maintained. The current density J on the left side has to be equal to the current density on the right-hand side. And so, because you have a difference in the conductivities, you can see that we have a higher slope, higher gradient of electrochemical potential in a semiconductor as compared to the metal. Okay, so basically what this means is that when we apply a voltage, we get almost all the voltage drop across the semiconductor. Now, what happens when we have a ferromagnetic metal? Again, we want to use this as our source for spin injection. Well, what happens, of course, is that if we want more spin-up electrons to flow in the semiconductor than spin down, then because the conductivity of the non-magnetic semiconductor is exactly the same for spin-up and spin-down, the electrochemical potential gradient has to be different. So here we have an electrochemical potential for spin-up, and it has a high gradient, giving rise to a higher current than for spin down. And this then results in electrochemical potential splitting at the interface. Okay, now we can write down a simple expression for the polarization, which is just the relative difference between the current flow for spin up and spin down. And what we find is that it's a function of the splitting in the electrochemical potential at the interface. Now, this splitting has to be continuous across the interface into the ferromagnetic metal, where it decays over a very short length scale due to the fact that the spin lifetime is actually very short in the ferromagnetic metal. Now we can therefore write down an expression for the splitting on the ferromagnetic side, and it's essentially driven by the asymmetry in the conductivity due to the fact that there's a difference in density of states for spin up and spin down in the ferromagnetic material. And of course, again, because the splitting has to be equal across the interface, we set these two expressions equal to each other, and we can solve for the polarization in the current that's flowing in the non-magnetic semiconductor. So without doing all the arithmetic, this is the result. We see that it's proportional to the bulk polarization in the ferromagnet, which we expect, but it's certainly not, the polarization is certainly not equal to the polarization in the ferromagnet. It's limited by this expression, this expression epsilon, which is the ratio between not only the conductivities of the semiconductor and the ferromagnet, but also the length scales that are involved. Now, what's important here is that, as I said before, the conductivity of a semiconductor is much smaller than the typical metals. And so this ratio here between the conductivity is very small. Not only that, it's also proportional to the ratio in the length scales. And because, at least in silicon, the spin lifetime is very long, the transport length scale in the semiconductor is also very long. And so this ratio is, once again, very much smaller than unity. So this epsilon is a very small quantity. And so the polarization of the current that flows in the semiconductor is very small unless the ferromagnetic bulk polarization is almost unity. Then it cancels out this one here, and the epsilon cancels out, and we can just push our polarization, our 100% polarization across the interface. This has not been achieved in reality, and so what happens is that this ohmic injection, just taking a spin polarized source of ferromagnetic metal and pushing electrons across the interface by applying a voltage drop, is not going to result in spin polarized current flowing in the non-magnetic semiconductor on the other side. So what we have to do is come up with a way around this problem. Of course, even after we analyze this problem, we would say, all we have to do is look at this. Let me go back here. All we have to do is notice that the problem that I just described is driven by the fact that the splitting of the electrochemical potential is the same on both sides. So what we should do then is we should allow the electrochemical potential splitting on the ferromagnet side to be much smaller than the electrochemical splitting on the non-magnetic semiconductor side by simply separating the two with a resistive material in between. But the only way for this to lead to a higher spin polarization injected in the semiconductor is if the conductivity of this interlayer that we insert at this interface is spin dependent. Now, the one way to achieve this is through tunneling. It turns out, of course, that the tunneling probability is dependent on the wave number, which is different. Excuse me. On the wave number, which is different for spin up and spin down due to the splitting of the band structure in the ferromagnet. And so one might propose, what we have to do is just take our ferromagnet and separate it from our semiconductor by a tunnel barrier, thin tunnel barrier of just a few nanometers, and then we'll achieve what we wanted. The problem here is that if the semiconductor itself is very lightly doped, or even undoped, as I'll show you, that there's no way to actually efficiently inject even charge. And the reason why is due to the discontinuity between the Fermi energy and the conduction band of the semiconductor. Now you might say, well, this is trivial. We can get electrons from the Fermi level of the ferromagnet into the conduction band of the semiconductor just by applying voltage. Then this Fermi level will rise because you're giving potential energy to the electrons, and then you'll get tunneling into the conduction band. But the problem here is that the semiconductor, being so lowly doped, has a very high resistance, and so you apply a voltage from this side to the next, and essentially all your voltage drops across the semiconductor and not across the barrier. And so we can't actually achieve this. This is essentially not going to work when we have very low intrinsic or very non-degenerate doping in the semiconductor. So with that sort of long-winded introduction to the general problem, I'm going to show you how we actually achieve this spin polarized electron injection into this non-magnetic semiconductor completely out of equilibrium. Okay, so I'll try to talk about a few of these topics. I'm going to try also to emphasize a few items here, a few issues, which I think will perhaps open the door for later discussions in which we can, by a mutual understanding of each other's research, sort of bridge the gap and encourage collaboration. Okay, so what I spoke about before was ohmic transport of electrons from metals into semiconductors. It turns out that the problems that I described are really fundamental to any kind of ohmic transport regime. And so the way around this fundamental limitation to spin injection is to use a different injection mode. We use ballistic hot electron transport, not only for injection, but of course later on for detection. After all, you could be injecting spin polarized electrons all day, but you'd never know it. You have to at some point make a measurement. You have to detect the spin after they're injected, move to somewhere else, and then come out of the system. Okay, so the idea here is that we're going to generate electrons that are in states that are not thermalized with the lattice. They're not even thermalized to themselves. So a kind of description which is dependent on this definition of electrochemical potential is really not appropriate. To give you an idea of how this works, consider just a simple tunnel junction. Two metals separated by a very thin insulator through which you can have quantum mechanical tunneling. This is again a band diagram so that we have energy on the vertical axis, distance on the horizontal. When I apply a voltage between these two metals, what happens is that the voltage bias gives potential energy to electrons in the cathode relative to the anode, and then electrons can tunnel from filled states at and below the Fermi level into unfilled states. Electrons from the cathode at and below the Fermi level can tunnel into empty states at equal energy in the anode. And at that point, they have much more energy than the Fermi level in the anode, and they're not thermalized to it. These are hot electrons. Now, we make use of ballistic transport through this anode such that we can collect the electrons which can travel a certain distance on the order of the mean free path before they inelastically scatter down to the Fermi level of the anode. How do we do that? Well, we place behind the anode, a thin film anode, a Schottky barrier. The idea being, of course, that if we apply a voltage across our tunnel junction injector, which has a ferromagnetic cathode, we then have more of spin-up electrons tunneling through the barrier. And these electrons couple with hot electron states in the anode. Most of them do suffer inelastic transitions and relax down to the Fermi level, but some of them can move ballistically through the anode, through the non-magnetic anode, and couple with conduction band states on the other side. And that's how we achieve our injection. The Schottky barrier here, this discontinuity between the conduction band level and the Fermi level, which is normally rectifying and keeps all of these thermalized electrons out of the semiconductor, is here used as an energy filter. It actually enables us to separate the electrons which are injected from the ferromagnet, the ones that are spin polarized, from the electrons that are below the Fermi energy, which are not. Okay? Now, what happens is that we're injecting these hot electrons very far above the conduction band edge. Once they cross over the interface into the semiconductor, they subsequently have to relax down to the conduction band edge by a cascade of phonon emission. But this occurs over a very short length scale, typically 10 or so nanometers. So what this means then is that throughout throughout most of the transport distance, which is typically several hundreds of microns, the transport occurs at the conduction band edge and is subject not only to drift in the presence of an internal electric field provided by a voltage drop between the anode of our tunnel junction injector and the other side where we detect, but also it's subject to the random motion of diffusion. I'll show you what the consequences of that are in a moment. Okay, so that's how we achieve the injection. How do we detect these electrons? Well, these electrons are at the detector side, ejected from the conduction band into a ferromagnetic contact. Now, keep in mind, once again, these electrons that are coming over a Schottky barrier. It's as if they're jumping off a cliff. And so they initially have a very high kinetic energy. So they're once again hot electrons, but they're hot electrons not in a non-magnetic anode. Here they're hot electrons in a ferromagnet. And so their mean free path, the inelastic scattering rate, if you will, is dependent on the relative orientation between the spin polarization of the electrons after they've traveled through all of the silicon and the ferromagnetic magnetization. Okay, so what that means is that in this case, if we're injecting spin-up electrons, if the spin is maintained in the up direction and the magnetization of our ferromagnetic detector contact is also up, then the mean free path will be relatively long, and the probability that the electron will pass ballistically through this ferromagnetic thin film and over another Schottky barrier on the other side into the conduction band of a second piece of silicon will be relatively high. If, on the other hand, we have an anti-parallel configuration, we inject spin up, but we have a detector magnetization that's down, then we'll have a shorter mean free path, stronger inelastic scattering, and the numbers of, or the rate of electron injection into the second piece of silicon will be low. So the current that's flowing in the reverse direction across this Schottky barrier is going to be our spin signal. It's going to be the indication that we have spin polarized electron transport through our undoped semiconductor channel. Okay, so one of the device geometries that we've employed to realize the band diagram that I've just shown you is a vertical geometry device. We've also applied this to lateral geometry devices in which we can, for instance, add another electrical contact, an electrode for electrostatic gating, in which case we can investigate the role of interfaces on the spin transport. But in this simplest geometry, what we do is we have we have a solid-state tunnel junction injector with a ferromagnetic cathode. We inject electrons ballistically through the anode contact, over the Schottky barrier, and into undoped silicon of several hundred microns. What we're doing is we're essentially injecting on one side of a wafer and detecting on the other side. Then after vertical transport through the semiconductor, electrons are ejected from the conduction band into the ferromagnetic metallic part of the detector, and some of them make it into an N-type silicon second collector, and that's where we measure our spin transport signal. Okay, so the simplest kind of measurement that we make is, as I described, just measuring the difference between injecting and detecting in a parallel and anti-parallel configuration. And we do this simply by using different ferromagnetic metals so that their coercive field is different. We sweep our magnetic field and we can obtain both a parallel orientation, in which case we have a relatively high second collector current, our spin signal. As we pass through zero magnetic field, though, one of the ferromagnets will orient its magnetization parallel to the magnetic field first, in which case we have an anti-parallel injector-detector configuration. Once again, enhanced inelastic scattering in the detector gives rise to a lower spin signal. Of course, continuing to increase the magnetic field on the other side will result in orienting both of the magnetizations with the magnetic field and recover a parallel spin signal. Of course, you see the same signal reflected about zero when you reverse the field sweep to reflect the ferromagnetic remnants in hysteresis. Okay, now these kind of measurements, of course, are very, very important because they allow you to make a measurement of the spin polarization of the electrons after they've traveled through the silicon. And so by varying the amount of transit time through manipulation of the internal electric field, we can then use that in a measurement of the spin lifetime. Of course, this kind of measurement, just making a measurement of the difference between parallel and anti-parallel magnetization to determine the polarization, is really not it doesn't tell you any more information. What we do, however, get a lot of information from is spin precession, and I apologize that I have a video here, but somehow it's not working. So previously what I showed you is that if you change the magnetic field in the device plane, we can switch the magnetization and the relative magnetization between the injector and detector spin axis. And we can see the result. Obviously, when we have a parallel injector and detector magnetization, we have a high spin signal, and when they're anti-parallel, we have a low spin signal. If, on the other hand, we orient the magnetic field perpendicular to the injector magnetization, the electron spin will be injected in the device plane, but it will feel the torque from the application of the magnetic field perpendicular to it. Inject the spin, apply the magnetic field. The spin will then rotate or precess around that perpendicular magnetic field. You guys should be familiar with this from spin resonance. Now, what happens, of course, is that each one of these electrons is being injected into the silicon with a definite spin orientation that's determined by the magnetization direction of the injector. And so the spin orientation accumulates a precession angle determined by the strength of the magnetic field, the strength of the perpendicular magnetic field, which determines the precession frequency, and the transit time, the amount of time it takes for the electron to get from the injector to the detector. And that, of course, is inversely proportional to the internal electric field. So we can determine this precession angle, theta, magnetic field or with electric field. So what happens when we do the measurement? This results on the same device where I showed you the so-called spin valve, where we're just changing the magnetization of the contacts. Here now, the magnetization of the contact is not changing because we're applying a perpendicular magnetic field. We have thin film ferromagnets, which have a very strong shape anisotropy. The magnetization always lies in the plane. So we're applying a perpendicular magnetic field. Magnetization doesn't change, but the influence of the magnetic field on the spin, independent of the magnetization, causes spin precession and the results I'm going to describe now. So the idea here is that if we have parallel injector and detector magnetization, then at 0 applied perpendicular magnetic field, there's no spin precession. And so we have a relatively high spin signal. But if we apply very small perpendicular magnetic field, due to the very long distance between injector and detector, then we can arrange it so that we inject spin up, but we have precession 180 degrees by the time it makes it to the detector. And so even though we're injecting spin up, measuring spin up, in the absence of precession, we would expect a large signal. But because the spin is rotating from up to down, we get a low signal at just about 10 or 15 Gauss. Now, this process is periodic, and so, of course, if we just double the magnetic field, then spin up is injected. It precesses, but it precesses all the way back to spin up again, and so we recover our higher spin signal. Of course, what we would expect just based on this simple understanding is that we would get a signal which is proportional to the cosine of the precession angle. And so we would expect that we could just increase the magnetic field and we would get infinite orders of oscillation due to precession through multiples of 2 pi. But what we see is as we increase the perpendicular magnetic field strength, that we do see the continued oscillation, but the strength, the amplitude of this oscillation decreases. And the reason for this is that, again, not only do we have the influence of the electric field, which drives the transport from injector to detector, in other words, charge and spin drift, but we also have the influence of the random motion of the electrons, the diffusion. And the diffusion causes an uncertainty in the angle, in the precession angle, through an uncertainty in transit time. And this causes spin dephasing. Now, of course, we can account for this simply by adding up all of these cosine contributions from electrons with a definite transit time by weighting with the transit time distribution for our spin current. And the transit time distribution for the spin current can be very simply modeled with the drift diffusion equation Green's function, or impulse response. And this model has several tunable parameters, the spin drift velocity and the spin diffusion coefficient. And we can change those parameters to fit our data. So that's the red curve here, and you can get pretty good correlation. But what we like to do even more is to be able to start with our data, our empirical data, and recover from it an empirical spin transport distribution without any model fitting. And it turns out you can do that as well because, of course, this is just the real part of the Fourier transform of the arrival time distribution. And so we can invert that transform, take the inverse transform, to recover the empirical transit time distribution for our spin current. So the idea here is illustrated here. Basically, what I'm showing you here in this inset are multiple spin precession measurements as we change the perpendicular magnetic field under the influence of different strengths of electric field. So at the bottom here, you see just a few oscillations with a very short magnetic field precession period. The reason why is because this corresponds to a small internal electric field, so it takes a very long time for the electrons to go from the injector to the detector. And so the spin precession frequency can be very small, and we'd still get very large precession angles. At the same time, because it takes a long time for the electrons to make it from the injector to the detector, the effects of diffusion are very strong, which gives rise to very strong dephasing. And that's why we only see a few oscillations before the signal just completely washed away. As we increase the electric field, though, what happens is, well, several things. The magnetic field period increases because the transit time is small. And so to get the same precession angle, you have to apply a larger magnetic field. But also, we see the fact that there's more oscillations. There's more oscillations because the effects of dephasing from diffusion are minimized. And if we take the transform of this data, then we can see the empirical spin current transit time distributions that result. And they, of course, correspond to our understanding in that both the mean of the distribution decreases under the influence of stronger electric fields because the electrons are moving faster, the drift velocity is faster, and higher electric fields. But also, the uncertainty in these distributions gets smaller and smaller because, once again, you're minimizing the effects of diffusion and hence dephasing. Now, one of the powerful things that we can do, let me go back. One of the powerful things we can do here is, since we can, by the use of these spin precession measurements, determine the mean transit time, we can then use these measurements in conjunction with in-plane magnetic field measurements to determine the spin polarization, to then see the relevant time scale for spin depolarization. So the idea is that we do these spin precession measurements, extract the transit time distributions, and determine the mean of those distributions. Obviously, as I showed you, as you increase the electric field, the transit time goes down. But simultaneously, we also make these spin valve measurements, which determine with which we can determine the spin polarization after transport. And what we see is that as we increase the electric field, the transit time decreases, but the polarization rises. This, of course, is due to a finite spin lifetime. And we can fit these data points and determine the time scale for spin depolarization. That's our spin lifetime. If we want to make an analogy with electron spin resonance, this is like a T1 time, except for the fact that this is a lifetime which can even be defined in absolutely zero magnetic field, because it's a return to equilibrium even in the absence of a Zeeman splitting. So the analogy is not quite exact. And of course, we can see the effects of changing the temperature due to the fact that the spin lifetime, although it's very long, is of course finite, and it's limited by the residual spin-orbit interaction, which results in spin flips through electron-photon scattering. Now, I want to point out here that these kinds of measurements were done in relatively small electric fields, where the system was more or less in equilibrium. This, as I described, the fact that the spin lifetime is finite is due to the fact that because there is a residual spin-orbit interaction, the eigenstates in the conduction band are not pure spin eigenstates. And what happens here is that the momentum scattering results also in a spin flip scattering that's proportional to that momentum scattering, and also proportional to the mixing amplitude, the mixing amplitude of the opposite polyspin wave function. You can use this simple kind of idea to determine the power law due to the presence of acoustic phonons, which cause intravalley scattering in the silicon, that determines the spin lifetime at low temperatures. But what I'm going to talk about next is some recent work in which we can see the influence of pushing the system out of equilibrium, literally determining the spin lifetime and the spin relaxation mechanism that's dependent on the transport process itself. Let me go back a second. Despite the fact that we can make these kinds of spin lifetime measurements by making a correlation between the spin transit time and the spin polarization, which is really nice, we haven't really learned very much more about spins in silicon than one could using electron spin resonance techniques. This kind of power law of spin lifetime has been known literally for decades from simply from line width measurements of absorption and resonance. And what I want to point out here is that we can influence the spin relaxation mechanism due to the transport process itself. So let me show you what I mean. Previously, as I said, we were using very low electric fields in which the electron ensemble was in equilibrium with the lattice. Now, what happens if I try to drive these electrons very, very strongly with strong electric fields? Well, if we look at this power balance equation, we see that as we drive large currents at large voltages, what we're doing here is we're dumping energy into the electron ensemble, and depending on its coupling with the lattice, we can actually drive an asymmetry such that the electron temperature rises with respect to the lattice bath that's held fixed. We can then invert this expression, this power balance expression, in order to determine the expected spin lifetime under these conditions. And when we do that, what we see is that we would, even under these very simple assumptions of this power law of the temperature that would determine the spin lifetime, what we see is an added factor here. We see the fact that not only would we expect the presence of an exponential spin decay, in other words, if it takes a longer transport times due to a finite static spin lifetime, this tau S0, but we also see a voltage dependence which would give rise to a decreasing polarization at very high, under the application of very high voltages. So in other words, the effect of heating the electrons with the electric field would be that instead of just shortening the time scale for transport much shorter than the spin lifetime and saturating the resulting spin polarization, you actually start to depolarize the electrons due to the electron heating effect with a characteristic voltage scale V0 here. Now, if I make a kind of analogy to charge transport, this would be like a spin gun effect. The gun effect in charge transport in semiconductors is this kind of counterintuitive reduction in drift velocity upon the application of large electric fields. What happens at low electric fields is everything behaves ohmically. We start increasing the electric field, and electrons just move proportionately faster with a kind of fixed mobility. But after a certain point, what happens is, in this gun effect case, you heat up these electrons. They move into secondary valleys, conduction band valleys, and they lose their kinetic energy, and so the electrons actually slow down. So this is a negative differential mobility. What I'm talking about here is a negative differential spin lifetime, where by increasing the electric field and getting a shorter transit time, you actually depolarize your electrons instead of retaining the spin polarization. So the question is, can we actually measure this? Well, with this kind of heuristic and overly simplistic model, which takes into account only acoustic phonon scattering that occurs within the same conduction band valley, we would calculate a voltage scale of 15,000 volts. So previously I showed you this kind of linear, sort of static response under application of several hundred volts. So I think it was something like 600 volts. So the question is, if we apply even stronger electric fields at higher voltages, would we actually see this negative differential spin lifetime? And the fact is we do. So here once again is a measurement of spin polarization as a function of transit time determined by spin precession measurements. And you can see here for the low electric field case, which corresponds to a long transit time regime, yes, we do have this. We can fit this with an exponential. It may look a little. Oh, this is a linear scale, so everything looks fine. So this is the fit of exponential decay with some reasonable spin lifetime, several hundred nanoseconds or so. But as I increase the electric field more and more, I do get a shorter transit time, but the polarization actually drops. And it drops no matter what temperature, no matter what lattice temperature I'm talking about. If we look at this this anomalous regime as a function of the voltage, not the transit time, then you can see we have this sort of quasi-linear regime, which we can compare to our exponential and extract a voltage scale, a comparison to this V0 that I showed you before. And maybe it's hard to read here, but essentially what happens is that we're measuring a voltage scale on the order of 1 kilovolt, not 15. So the question is, what's going on? Well, the point here is that instead of just the intra-valley scattering, which takes you from a state in one of the 6-fold degenerate conduction band valleys in silicon to another one, say very small momentum scattering that would give rise to this power law spin decay. If you instead now consider the effect of a field-induced inter-valley scattering, specifically a F process in which you take an electron in one conduction band valley and scatter it into another one with an axis that's perpendicular to its initial state, then you can get very strong spin depolarization. Essentially what's going on here is, instead of the static electron depolarization, which can be thought of essentially as the result of phonon absorption, here now we're giving the electrons a lot of kinetic energy. We're heating them with our electric field, and they're shedding this kinetic energy and momentum through phonon emission. And it's very efficient for them to do this with a large momentum F process phonon carrying from one state in one conduction band valley to another, which results in the spin depolarization that we see. One of my theory colleagues has implemented a Monte Carlo in order to make a direct comparison. And one of the most relevant aspects here is the fact that even though we see very strong temperature dependence in essentially zero electric field, sort of static case, with the application of relatively small voltages, you can substantially change the effective spin lifetime of these electrons. And from this kind of modeling, you can determine then a prediction that indeed the appropriate voltage scale for spin depolarization from this field-induced phonon emission is on the order of what we measure. So several hundreds to thousands of 1,000 volts. Okay, so I want to talk to you maybe one more topic. I hope it's okay if I'm running a little bit late. I apologize. Something that maybe is even more relevant to the kinds of things that you guys are doing with electron spin resonance. In this case, I'm going to talk about measurements in where the silicon is not intrinsic or nominally intrinsic, or at least undoped as before, but now the case in which we have an intentional doping of the silicon. In this case, the first consequence of the doping is that the presence of the ionized impurity gives rise to band bending, just from the electrostatics of the problem. So we're once again injecting spin polarized electrons using a hot electron tunnel junction source, and we're detecting them by looking at the asymmetry and inelastic scattering in a ferromagnetic thin film. But in between, now we have, of course, a band bending due to the confluence of depletion regions from one Schottky on the left and another Schottky contact on the right. But not only that, we also leave behind the impurity states, and we think we see the effects of these impurity states. So let me show you now, once again, spin precession measurements. So we're injecting spin that lies in the device plane, and we're detecting spin that lies in the device plane, but we're applying a perpendicular magnetic field. And so, as I showed you previously, our interpretation of these of our measurements is that what we're really measuring is the Fourier transform of the arrival time distribution. Now, you guys, I'm sure, know that there's this reciprocal relationship with a Fourier transform, so that the magnetic field scale of features that we measure is inversely proportional to the time scales that cause them. Just like I showed you previously, the oscillations in the spin precession get much larger when the transit time gets smaller. Likewise, the envelope of these cosine-like oscillations gets wider as the uncertainty in the distribution gets smaller. So when we make measurements on these phosphorus-doped silicon transport devices, we see data that looks like this. It has now two magnetic field scales. It has a very large magnetic field scale. You can see here that at relatively large magnetic fields, we maintain a large spin polarization. Maybe I should explain this a little bit more. Essentially, what's happening here is that as we're applying our perpendicular magnetic field and sweeping it in the red from left to right and in blue from right to left, eventually, and you can see this happens at around 700 Gauss, a very small unintentional misalignment of the device normal with the application of a magnetic field causes a magnetization reversal that lies in the plane. Nevertheless, what we see is that up until that point, there's a drastic separation between the parallel and anti-parallel magnetization configurations. So this higher spin signal corresponds to essentially a mostly parallel spin, and blue corresponds to mostly parallel spin to detector magnetization, and blue is anti-parallel. So we see a very large magnetic field scale, which then would correspond to a very short transit time scale. But we also see at small magnetic fields, obviously a very small magnetic field scale, which would correspond to very long transit time effects. And we can see the effect of this when we apply internal electric field by changing the voltage from injector to detector. And we can also especially see a drastic change when we change the temperature. So this is now just an analysis of the polarization of this spin precession signal for the small magnetic field scale. And what we see is that as we increase the increase the temperature, the short transit time effects are minimized, and the relative strength of the short transit time effect and long transit time effect is obviously changing. So what's this due to? Well, our interpretation of this result, due to the fact that we have the presence of these impurity states, is that electrons are being injected and they're traveling through the conduction band, but every now and then what's happening is these electrons are being trapped. They're being trapped in these states that are just below the conduction band edge, and they're staying there for some amount of time before they're thermally excited back out into the conduction band. And what we measure on the other side of the detector, of course, are electrons which are passing straight through and not affected by this trapping and re-emission process, but also electrons which are trapped once, electrons which were trapped twice, and which have a distribution of trapping times, in other words, dwell times in this trap. And all the while they have maintained their spin polarization, and they've also been maintaining the precession under the influence of the magnetic field the whole time. And this is essentially giving us a means to clock or to time the transport distribution. Now, this is why you may have noticed in a previous slide I described our ability to convert between the magnetic field measurements we make and the times and the transit time distribution as a Larmor clock. Essentially, under the influence of this Larmor precession with the magnetic field, the electrons spin is actually acting like the hands of a clock. We're injecting electrons all set to 0 time, and the hands of the clock start moving, and we measure the angle of the hands of the clock at the detector. So they retain their measurement of what's happening in between injection and detection. Now, if we essentially sum up over all the contributions from all the possibilities for electrons to be trapped in one of these impurity states and then come out any number of times given some fixed number of traps, then we can model this effect. And what you see is that we can recover this sort of temperature distribution due to the fact that the re-emission process is, of course, thermally excited. Now, this part, I think, is perhaps most relevant to some of the work that you're doing here, simply because it, I think, naturally brings up the question of whether there's an interaction between not only between the electrons which are between the conduction band states and the impurity traps, but also is there a natural interaction between electron spins that are filling the conduction band states and the neutralized donor, which is holding for a very short period of time spin polarized electrons in a localized state. Perhaps even there's an interaction between the spin polarized electron in the impurity and the nuclear spin of the phosphorus as well. But these sorts of questions, I think, have to be answered in the context of electron spin resonance and are very difficult and perhaps even impossible to probe using the transport experiments that I've described here. I think I'm probably out of time, and I don't want to perhaps bore you, but I'll just point out that here, just very quickly, that as I mentioned, we are also able to probe other aspects of spin polarized electron transport out of equilibrium here in a different kind of geometry in which we have injector and detector, which are no longer vertically oriented but now laterally oriented on the same side of silicon, so that during transport laterally we can influence their interaction with the interface between silicon and silicon dioxide below it by using the dope substrate as an electrostatic gate, pull electrons to this buried interface, where, just to sum up very quickly, we see the influence of what we think are paramagnetic impurities, which are giving rise to very strong spin scattering, spin depolarization, once we pull electrons closer to the interface. So basically what this shows here are the spin current transport distributions under the influence of the gate voltages that you see here. So with more positive gate voltages, we're pulling electrons closer to that interface, and we see a depolarization, which gives rise also to an apparent shortening of the transit time. And this has been recently modeled using two-dimensional finite differences, in which we can say that the interfacial spin lifetime is actually orders of magnitude shorter than the bulk spin lifetime that we've seen in vertical transport devices. So it's a very strong effect that we can control with the application of electric field in this lateral transport geometry. Okay, so I'll just end there, and I hope that what I've said here maybe get your thoughts moving at the very least towards perhaps discussions that we can have later, and maybe connect the dots between what you're doing and what we're doing to be able to do something that perhaps neither one of us can do individually. So thanks very much.